Okay, so get this. We've all heard about how amazing AI is getting, right? Especially these large language models. But what if I told you that even the most advanced ones, they might be failing like a basic physics test?
Yeah, that's exactly what this new research paper is suggesting, and it's causing like quite a stir in the AI community.
I knew this deep dive was going to be juicy. So our source material today is this paper. It's called The Stochastic Parrot on LLM's Shoulder, a summative assessment of physical concept understanding. Break it down for me. What's a summative assessment, and why does it matter for AI?
Okay, so think of it this way. You're learning to drive, right? A summative assessment isn't just about whether you can, recite the rules of the road. It's about whether you can like actually apply them, like in a real driving test.
Okay.
Same idea here. The researchers wanted to see if LLMs could go beyond just memorizing facts about physics and actually like demonstrate that they understand it.
So they're not just testing if the AI can talk the talk, but if you can walk the walk, right? When it comes to physics, I like it. Tell me more about this assessment that they cooked up.
Sure. So they designed a test. It's called PhysiCo, and it specifically focuses on, how well LLM can grasp these physical concepts. And the clever part is they built in two levels to it, low level and then high level understanding. So low level is like, can the LLM define gravity or explain what a lever does? Just basic stuff.
Okay, so that's like the AI proving it paid attention in physics class. What about the high level stuff?
Yeah, so that's where things get really interesting. High level understanding is about, taking those concepts and then actually applying them to like problem solving scenarios. So can the LLM figure out how a pulley system works or predict the trajectory of a ball rolling down a ramp? Things like that.
That sounds like a pretty tough exam. How did the researchers make sure it was like a fair fight, though? I mean, LLMs are trained on text, right? How do you test their physics knowledge without just giving them a textbook to just regurgitate?
Right. Well, that's where the researchers got really creative. So instead of using like text-based questions, they presented the physics problems visually in grids. They kind of looked like simple matrices.
Grids, that seems a bit out of left field. Why grids?
Yeah, it's actually a brilliant strategy because LLMs, they're amazing at recognizing patterns in text. So giving them a physics problem written out in words, they might be able to just rely on those memorized patterns. But by using grids, which are less common in their training data, it forced them to like demonstrate a deeper understanding of the concepts, not just pattern matching.
Ah, so like giving them a puzzle that they've never seen before to see if they can apply the principles that they've learned. Sneaky. So how did the LLMs do? Did they pass with flying colors?
Well, on the low-level understanding tasks, yeah, they totally aced it. We're talking like above 95% accuracy. They could define terms, explain basic concepts. They clearly had all that textbook knowledge down pat.
Okay, so they could definitely pass a written exam. But what about when it came to actually solving those tricky physics problems, right? How'd they do on the high level stuff?
Yeah, that's where things took a turn. On those high-level tasks, using the grids, their performance just plummeted. They lagged way behind how humans performed on the same problems. And we're talking humans scoring above 90%, while the LLMs were struggling to even get close.
Wow, that's a huge difference. So are we saying that these super smart LLMs are actually kind of clueless when it comes to like real world physics? Or could it be that the grids were just throwing them off?
That's a great question. And the researchers actually anticipated that criticism. So they wanted to make sure that it wasn't just a matter of the LLMs being unfamiliar with the format. So they tried a few things to give the LLMs like a boost.
Okay, so they gave the LLM some extra help. Like, what did they do?
Yeah, so first they tried what's called in-context learning, and that's basically just giving the LLM some examples of how to solve similar problems using the grids. So, think of it like showing them a few worked out practice problems before the test.
Okay.
And then they went a step further and they tried what's called fine-tuning. And that's like giving the LLM specialized tutoring sessions, and these were focused specifically on solving problems that were presented in that grid format.
So they basically gave the LLMs every advantage they could think of.
Exactly, but here's the kicker. Even with all of that extra help, the LLMs, they barely improved. Their scores on those high-level tasks, they remain significantly lower than human performance.
That's fascinating. Like they can memorize the entire physics textbook, but can't figure out how to use that knowledge when they're faced with a real world problem. So does this mean that LLMs are fundamentally flawed? Are we like putting too much faith in them?
It definitely raises some important questions about the nature of, AI understanding. But before we jump to any conclusions, let's not forget that this research, it focused specifically on text-based LLMs. There's a whole other world of AI out there that might perform differently.
You're talking about multimodal LLMs, right? The ones that are trained on images and videos as well as text. Maybe they'd have an easier time with those visual physics puzzles.
Yeah, that's what the researchers wanted to find out. So they tested one of the most advanced multimodal models, GPT-4AM, and it did show some improvement on certain grid tasks, particularly when the problems were presented with images instead of just the matrices.
So giving the AI a visual aid helped a bit. That makes sense. But did it manage to catch up to human performance?
Well, here's where it gets really interesting. Even with that visual boost, GPT-4o still couldn't quite match human performance on the physics problems, especially when it came to those more kind of abstract conceptual tasks. It seems like even having access to both text and images wasn't enough to really bridge that understanding gap.
So even our best multimodal models are still falling short. That's kind of mind-blowing when you think about how much progress we've made in AI. What does this mean for the future of AI development? Are we on the wrong track here?
I wouldn't say we're on the wrong track, but this research definitely challenges, some assumptions we've been making. For a long time, the focus has been on building like bigger, more complex models, feeding them massive amounts of data and seeing what they can do. But this study kind of suggests that something fundamental might be missing.
It's like we've been so busy teaching AI to sound intelligent that we've overlooked the importance of true understanding. But if bigger isn't always better, where do we go from here? What are some of the potential paths forward for developing AI that can like truly grasp these complex concepts?
Well, whoa. Hey, welcome. What's up?
Yeah, as you say, so what's the fundamental key for the AI to understand the physical world?
That's the million-dollar question. I think that at a fundamental level, AI needs more than just data. It needs a way to reason.
Yeah, it's not enough for them to just recognize patterns, but it needs to understand cause and effect. It's what those PhysiCo tests were trying to get at.
Exactly. And that gets us to the question of LLM architectures and if they can be specifically designed for reasoning. As right now, most LLMs are optimized for generating fluent text, which is amazing, but it doesn't necessarily translate to, deep understanding.
So we need to shift our focus from making AI sound human to making it think more like a human. How do we even begin to do that?
Yeah, it's a tough challenge, but there are some promising avenues being explored. For example, some researchers are experimenting with incorporating what's called symbolic reasoning into LLMs, and this involves, representing knowledge and logic in a more formal, structured way, almost like giving the AI a set of rules and principles to work with instead of just a massive sea of data.
It's like teaching them the grammar of thought, not just the vocabulary. I'm trying to wrap my head around this. So instead of just recognizing patterns in the data, we're giving them the tools to actually reason and make logical deductions.
Exactly. And there's also a lot of excitement around what's called neurosymbolic AI, which aims to combine the strengths of both approaches. It's like trying to build a bridge between the pattern recognition power of neural networks and the logical reasoning capabilities of symbolic systems. And it's still early days, but this hybrid approach has the potential to create AI that can both learn from, massive data sets and make sense of the world in a more human-like way.
That sounds really promising. But let's be real here. Teaching a machine to understand the world as deeply as humans do, that's a monumental task. I mean, we've been evolving and learning for. Is it even realistic to think that we can replicate that in a machine?
You're right. It's a daunting challenge, and I don't think anyone expects, a quick fix. But what's so exciting about this field is that we're finally starting to ask like the right questions. It's not just about, throwing more data at the problem or building bigger models. It's about fundamentally rethinking how we approach, AI development.
It's like we've been so focused on building the world's most powerful calculator that we forgot that we actually need a philosopher. So if we want to move beyond these, stochastic parrots, we need to start thinking more about how humans learn and understand the world. Are there any specific areas of human cognition that researchers are looking to for inspiration?
Absolutely. There's growing interest in incorporating insights from from developmental psychology and cognitive science into AI research. Instead of treating AI as just like a blank slate, researchers are starting to study how children develop their understanding of the world, how they learn language, how they reason about cause and effect, all of these things.
So it's like AI is going through its own kind of childhood, learning and developing, just like we do. That's a fascinating analogy. But this all sounds incredibly complex. Are there other hurdles beyond just the technical challenge?
Hey, yeah, what's up?
Does this paper refer to the reinforcement learning? Sets the AI into the physical world. Use the reverse RL to learn the fundamental of the concept.
That's a great question. Well, this paper doesn't specifically focus on reinforcement learning. You're right that it's another key approach.
Yeah, you're onto something important. It's all about how AI interacts with the world.
So reinforcement learning, or RL, is definitely relevant here.
How so?
Well, RL is all about training an AI agent through trial and error in an environment.
So the AI learns by doing and gets rewarded for making the right choices.
Exactly, and reversible RL is fascinating.
Yeah. As you say, RL allows for a constant feedback loop.
Now, the PhysiCo benchmark is more of a summative evaluation of what an LLM already knows.
Right, it's testing their existing knowledge, not necessarily how they learn.
However, you could totally use reinforcement learning to train an AI on the PhysiCo tasks.
That's a cool idea, using reversible RL in grid world situations. That's a great question. I'm not seeing anything in this paper about reinforcement learning directly.
However, that doesn't mean it's not relevant. You're right. That is how AI interacts with the physical world.
So reinforcement learning is like letting the AI experiment and learn from its mistakes.
Right, exactly. But this paper is more about testing existing knowledge using the PhysiCo tests that we discussed.
Okay, so with that said, there are other hurdles, like are there society or ethical considerations?
Absolutely. And it's something that we need to be thinking about as we develop AI that can truly understand. It could learn to solve those visual physics puzzles through interaction.
Okay, let's not forget where we were headed.
Right. Now, beyond of the technical challenges, we also need to consider societal implications.
You've hit on a crucial point. The development of AI has enormous societal and ethical implications.
It's not just a matter what can we do it, it's should we do it and how do we do it responsibly.
Right, we've all seen those sci-fi movies where AI becomes self-aware. I think it's easy to get caught. Oh yeah, let's hear it.
Absolutely, I can do that for you.
Yeah, no problem. Let's bring it all together.
Okay, so to summarize, this paper confirms the stochastic parrot issue.
Right, LLMs are great at memorizing, but struggle with true understanding.
Exactly, and PhysiCo is just the beginning of assessing what AI knows.
So this has implications for how we develop AI going forward.
And that brings us to another crucial point.
What are the broad takeaways regarding AI and its future?
The key takeaway is that the question of AI is more complex.
Right, it's not just about whether AI is smart or dumb.
Exactly, and that path requires not just tech advancements.
It's about building a future where AI and humans collaborate.
For our listeners, I think the most important message is to stay engaged.
Like we're all on this journey of discovery together.
Well said.
This has been an incredibly insightful deep dive.
Yeah, and what's fascinating